Hello, everyone. Welcome to Pre-Lecture 20. This is going to be our second lecture in Chapter 15, talking about solubility equilibria again. Okay, so one of the things that we talked about last class, in fact, the main thing was KSP and sparingly soluble salts. So that means, of course, our reactants are going to be some sort of solid that dissociates into ions as products, right? And so in this example, we have silver iodide. It separates into silver plus, iodide minus. And we're going to talk in this pre-lecture about one of the things that might affect that solubility, and that would be a common ion. So for example, say we had this silver iodide, and we dissolved it in a solution that also contained another species, but a species that's fully soluble, such as sodium iodide. That would mean that the solubility of silver iodide would decrease due to the presence of a common ion. And so we could think of that as in terms of our equilibrium in Le Chatelier's principle, where if we're not starting with a concentration of 0 iodide on our product side, that means that we're going to move our reaction to the left, right, towards our reactants. And so a common ion will decrease the solubility of a partially soluble or sparingly soluble salt, okay? So here's a question for you. Which of these species would decrease the solubility of magnesium hydroxide? So take a moment, think about that. And the answer is these first two, magnesium chloride and potassium hydroxide. The way you would figure that out is if magnesium hydroxide is sparingly soluble, that means it dissociates into Mg2 plus, OH minus, and in these two instances, magnesium chloride would produce Mg2 plus, and so that is a common ion, and KOH would produce OH minus, which is another common ion, right? Sodium nitrate doesn't affect it. Magnesium hydroxide is itself a solid, and if it's already in a saturated solution, it's not going to decrease the solubility of magnesium hydroxide because it is just going to be present as a solid, right? Okay, so that is the common ion effect. Another thing that we're going to touch on in this pre-lecture video is something that we've actually talked a little bit about before. It has to do with definition of acids and bases. So a lot of chapter 14 was focused on Arrhenius and Bronsted-Lowry acids and bases. Now we're going to talk more about Lewis acids and bases. So this last definition here. And so this is not defined in terms of protons, but instead in terms of electron pairs. And so a Lewis base is going to be something that donates an electron pair, whereas a Lewis acid is something that receives that electron pair, okay? So some examples here, if we have aluminum and ammonia, we can form a Lewis acid-base complex, or if we have trichloroborane and diethyl ether, we can also form a complex here. And so a question for you is, what is the acid? What is the base? Hopefully you were able to get this. Lewis acid is going to be the thing that accepts our electron pairs. So our aluminum with our 3 chlorides is going to be our Lewis acid. Our ammonia is going to be our Lewis base. And then in this bottom example, boron is going to be what accepts our electron lone pair from our ether, goes right there. And our ether is the thing that donates that electron pair through that oxygen, okay? So this leads to the formation sometimes of complex ions, which is another name for coordination complexes, like we talked about in experiment 13 in lab this semester, where we had our cobalt complexes that were also coordination complexes. We could have also called them complex ions, where we have one or more ligands, bound to our central metal cation, okay? So that central metal, and generally speaking, metals or things with positive charges, when they're ions, will be Lewis acids because they will accept electron pairs, whereas things that have electron pairs to donate will be Lewis bases. Those will also be ligands typically, right? So an example we can think about here, say silver. So silver plus can react with ammonia, NH3, to make the complex ion AgNH32 plus. So our ammonia, if we were to draw out Lewis structures for these, they would have an electron lone pair that can donate into our Lewis acid, that is our silver plus, to form this complex ion. If we were to write our last type of K expression for this is Kf. So it is a formation constant, K. Then it's the same thing as always, products over reactants raised to their powers. So that's our product, reactants raised to the powers. And what's typical with formation constants is they tend to be very large. So we're used to having maybe 1.7 times 10 to the negative 7th. But in these examples, pretty much always going to be an exponent with a positive value, meaning that products are greatly favored, right? And so we can use this as chemists to our advantage, where if we have many quote unquote insoluble metal cations, so typical ones are like silver, aluminum, copper, lead, they will generally form complex ions very favorably. And so if we are able to add a Lewis base to our solution, that may help us increase our solubility. And so an example, silver chloride, something that has a KSP value of 1.6 times 10 to the negative 10th, so quite insoluble, right? That means our reactants are very favored. But if we dissolve that in a solution that contains ammonia as well, we can form our complex ion, which has a KF value of 1.7 times 10 to the 7th. And so if we couple those two equilibria together, we can calculate an overall equilibrium constant, K, by multiplying these two equations together. And so K, our overall K, would be equal to KSP times KF, which is what is shown here. And so overall, our now equilibrium constant is 2.72 times 10 to the negative 3rd. And so overall, take-home point is that our silver, Ag plus, becomes much more soluble in the presence of ammonia, right? And so these are examples of formation constants, Kf values. And again, if you look at all of these, they all have a positive exponent here. My favorite one in particular, iron hexacyanide, 2 times 10 to the 43rd, which is just like crazy, like times 10 to the 43rd, get out of here. That's a huge number. So very favorable formation of that product, okay? So that's it for the pre-lecture. If you have any questions, please feel free to let me know. Otherwise, I hope you have a great rest of your day, and I will see you soon.